With the unprecedented expansion of Internet usage, impending shortage of IP address availability was recognized by 1992 as a serious limiting factor to the continued usage of the Internet run on IPv4. In 1994, the Internet Engineering Task Force, the IETF, initiated the design and development of a suite of protocols and standards now known as Internet Protocol Version 6, or IPv6. As a worthy tool to phase out and supplement IPv4. IPv6 uses a 128-bit address size compared to the 32-bit system used in IPv4. That's 340 undecillion addresses, which is 340 with 36 zeros behind it, far greater than the 4.3 billion maximum addresses available for IPv4. This large address space has been designed to allow for multiple levels of subnetting and address allocation from the Internet backbone to the individual subnets within an organization, and prolongs the need to implement something like NAT. The preferred format, although not the ideal format, for writing an IPv6 address is x:/x::x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:x:x::x::x:x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:/x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x:x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x x with each X consisting of 4 hexadecimal values. The ideal method is to omit leading zeros and use a double colon to replace any single contiguous string of one or more 16-bit segments, or hextets, consisting of all zeros where the double colon can only be used once within an address. Otherwise, there would be more than one possible resulting address. This is commonly known as compressed format. IPv6 also has one of the spiffiest header formats in town, as it's designed to keep overhead to a minimum by moving both non-essential fields and optional fields to extension headers that were placed after the IPv6 header, allowing it to be more efficiently processed at intermediate routers and easily add new features. The header's flow label field also allows for better support of prioritized delivery. IPv6 supports both stateless and stateful address configuration in the absence or presence of a DHCP server. When DHCP version 6 or SLAAC is used, the local router's link local address will automatically be specified as the default gateway address. Link local addresses are used to communicate with other devices on the same local link. With IPv6, the term link refers to a subnet. Link local addresses are confined to a single link. Their uniqueness must only be confirmed on that link because they are not routable beyond that link. In other words, routers will not forward packets with a link local source or destination address. IPv6 has built-in security with header extensions that ease the implementation of encryption, authentication, and virtual private networks. IPsec functionality is basically identical in IPv6 and IPv4, but one benefit IPv6 has that 4 doesn't is that IPsec can be utilized along the entire route from source to destination. The Neighbor Discovery Protocol for IPv6 replaces the broadcast-based Address Resolution Protocol, ICMP version 4 Router Discovery, and ICMP version 4 Redirect messages with efficient multicast and unicast neighbor discovery messages. There isn't a date to move to IPv6 yet, so both IPv4 and IPv6 are expected to coexist for the foreseeable future. However, the IETF has created various protocols and tools to help network administrators migrate their networks to IPv6, which can be divided into 3 categories. There's dual stack, which allows IPv4 and IPv6 to coexist and run their protocol stacks simultaneously on the same network segment. Tunneling is a method of transporting an IPv6 packet over an IPv4 network. The IPv6 packet is encapsulated inside an IPv4 packet, similar to other types of data. Translation. The Network Address Translation 64, or NAT64, allows IPv6 enabled devices to communicate with IPv4 enabled devices using a translation technique similar to NAT or for IPv4. An IPv6 packet is translated to an IPv4 packet and vice versa. There are three types of IPv6 addresses. There's unicast, which uniquely identifies an interface on an IPv6 enabled device. Multicast, which is used to send a single IPv6 packet to multiple destinations. Anycast, which is an IPv6 unicast address that can be assigned to multiple devices. If a packet is sent to an anycast address, then it is routed to the nearest device having that address. Unlike IPv4, IPv6 does not have a broadcast address. However, there is an IPv6 all nodes multicast address that essentially does the same thing. IPv6 also has global unicast addresses, which are similar to public IPv4 addresses. Another type of unicast address is the unique local unicast address. IPv6 unique local addresses have some similarity to RFC 1918 private addresses for IPv4, but there are significant differences. Unique local addresses are used for local addressing within a site or between a limited number of sites. These addresses should not be routable in the global IPv6 and should not be translated to a global IPv6 address. Unique local addresses are in the range of FC00:7 to FDFF:7. With IPv4, private addresses are combined with NAT/PAT to provide a many-to-one translation of private to public addresses. This is done because of the limited availability of IPv4 address space. Many sites also use the private nature of RFC 1918 addresses to help secure or hide their network from potential security risks. However, this was never the intended use of these technologies, and the IETF has always recommended that sites take their proper security precautions on their internet-facing router. Unique local addresses can be used for devices that will never need or have access from another network. The IPv6 Global Unicast Address, or GUA, are globally unique and routable on the IPv6 Internet. These addresses are equivalent to public IPv4 addresses. The Internet Committee for Assigned Names and Numbers, the ICANN, the operator for IANA, allocates IPv6 address blocks to the 5 RIRs. Currently, only global unicast addresses with the first 3 bits of 001 or 2000:3 are being assigned. In other words, the first hexadecimal digit of a GUI address will begin with a 2 or a 3. This is only 1/8 of the total available IPv6 address space, excluding only a very small portion for other types of unicast and multicast addresses. The 2001 0DB8/32 address has been reserved for documentation purposes, including use in examples. A global unicast address has 3 parts: the global routing prefix, which is the network portion that is usually assigned by the ISP subnet ID, and there's also the interface ID, which is the host portion. Unlike IPv4, in IPv6 the all zeros and all ones host addresses can be assigned to a device. The all ones address can be used due to the fact that broadcast addresses are not used within IPv6. The all zeros address can be used, but is reserved as a subnet router anycast address and should be assigned only to routers. Stateless Address Autoconfiguration is a method that allows a device to obtain its prefix length, default gateway address, and other information from an IPv6 router without the use of a DHCP version 6 server. Using SLAAC, devices rely on the local router's ICMP version 6 router advertisement messages to obtain the necessary information. IPv6 routers periodically send out ICMP version 6 RA messages every 200 seconds to all IPv6 enabled devices on the network. An RA message will also be sent in response to a host sending an ICMP version 6 router solicitation RS message. IPv6 routing is not enabled by default. To enable a router as an IPv6 router, the IPv6 unicast routing global configuration command must be used. but it can be configured on a router without it being an IPv6 router. The show interface command displays the MAC address of the Ethernet interfaces. The IEU64 uses this MAC address to generate the interface ID for the link local address. Additionally, the show IPv6 interface brief command displays abbreviated output for each of the interfaces. The up output on the same line as the interface indicates the layer 1, layer 2 interface state. This is the same as the status and protocol columns on the equivalent IPv4 command. The link local address of the router interface is typically the default gateway address for devices that link on the network. The IPv6 global unicast address configured on the interface is also installed in the routing table as a local route. The local route has a -128 prefix. Local routes are used by the routing table to efficiently process packets with the destination address of the router's interface address. The ping command for IPv6 is identical to the command used with IPv4, except that an IPv6 address is used. IPv6 multicast addresses are similar to IPv4 multicast addresses. Recall that a multicast address is used to send a single packet to one or more destinations. IPv6 multicast addresses have the prefix FF00/8. Multicast addresses can only be destination addresses and not source addresses. There are two types of IPv6 multicast addresses. The assigned multicast are reserved multicast addresses for predefined groups of devices. An assigned multicast address is a single address used to reach a group of devices running a common protocol or service. Assigned multicast addresses are used in context with specific protocols such as DHCP version 6. Assigned multicast addresses. Two common IPv6 assigned multicast groups include the F2202-1 all nodes multicast group. This is a multicast group that all IPv6 enabled devices join. A packet sent to this group is received and processed by all IPv6 interfaces on the link or network. This has the same effect as a broadcast address in IPv4. The FF022 all routers multicast group. This is a multicast group that all IPv6 routers join. A router becomes a member of this group when it is enabled as an IPv6 router with the IPv6 unicast routing global configuration command. A packet sent to this group is received and processed by all IPv6 routers on the link or network. Another type of IPv6 multicast addresses are the solicited node multicast. IPv6 enabled devices and ICMP version 6 router solicitation messages, or RS messages, to all the routers multicast address. The RS message requests an RA message from the IPv6 router to assist the device in its address configuration. Solicited node IPv6 multicast addresses are similar to the all nodes multicast address. The advantages of a solicited multicast address is that it is mapped to a special Ethernet multicast address. This allows the Ethernet NIC to filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the process is the intended target of the IPv6 packet. Alright, well, that appears to be everything I could dig up on IPv6 and cram into 15 minutes. I'm sure there's lots more, but again, this assignment is only for like 15 minutes. Could probably talk about IPv6 for a year or two, given all the complexities involved in it. Now it's time for me to do some doodles.